So recording has started. Okay, so I'm still explaining what we have, the material we have, so that I can know where to reference when I mention. Then the third one is the SWIM software. The fourth folder you have in your material list is the SWIM folder. Now, SWIM is from EPA, Environmental Protection Agency of the United States. They have a couple of free softwares. EPANET is also there, it's also free. Now, the concept of using free open softwares is because we'll find out that most of these advanced softwares always fall back on the engine of some of these free softwares. So if you learn how to use SWIM very well, it will be easy for you to adapt AutoCAD Civil SSA. It's the same interface, it's the same tools, it's the same protocol, it's the same algorithm. So, but the base, the default, just like we have AutoCAD, we have Revit, we have BritArc, and all the rest of them. SWIM interface is like the basics that will show you how to model using software. But let me say this also, and I always like to tell engineers this. There's no software that will do design for you. Softwares don't do design. What software does is to model your design and to simulate it. Is to model and I can't help but emphasize that. Because when people say, which software are you using in designing? It is you, the engineer, that will do the design. But you will now use software to control yourself, to check yourself. So what software does for you is to see if you are doing the right thing. Then in simulation, it also helps you to move back and forth in time, in temporary space. Okay, what will the discharge be if we have a 25-year rain? What would the discharge be if we have a 50-year rain? What would the discharge be if I have a 5-year rain? So the software will help you, instead of you starting all over again, it will help you to simulate different scenarios. So keep that at the back of your mind. No software does design. What the software does is to model and simulate. Then the next manual is the user manual for SWIM. That would, if you want to go higher, some master's students from University of Abuja have tried to come around and they've done design in terms of contaminant flow and everything, and they try to use SWIM and then combine it with other proprietary softwares, and they make comparison. Then the big man in the house is the urban design lecture materials. That's the sixth and the final folder you have. That is where you have the lecture materials on this course as captured from University of Stuttgart. That's our base, that's where we mirrored our program from. So we use some of the things that have used, we see some of their concepts, some of the methodologies. So there, we're going to be talking about rational method. We'll have a chart of rational method. We'll talk about hydraulics. Then we'll talk about urban drainage as a whole. Then we'll talk about hydrology. Now, when we talk about drainage, drainage is in two sectors. You have the sewer drainage system network. Then you have the stormwater system network. The sewer system, or you call it the foul sewer, or you call it the sanitary sewer, or you call it wastewater, they are all the same thing. These words can be used interchangeably. So whether you call it sanitary sewer, you call it foul sewer, you call it, or you just call it sewer, or you call it wastewater, they mean the same thing. Then the other one is storm drainage, or storm sewer. Okay, and sometimes in advanced countries they have combined system, but those systems are rare. In Nigeria, you can't try it. So in Nigeria, what we have are separate systems. You know, a separate system means there is a sewer line, foul sewer line coming from the houses, coming from human activity, going to a wastewater treatment plant. Then you have the separate sewer coming from stormwater, which are also going into the open water, open river. or swells, or what we call detention ponds, or any kind of structure that might be improvised to hold them for a while before discharging them, because some of them are highly concentrated, even though they are storm. They are coming from roads, from rooftops, from street and everything. Based on where they're coming from, sometimes they can be highly contaminated. So there will always be need to hold them and then allow them to decant, and then you kind of apply simple filtration to it, so that when they are being discharged into the water bodies, they will not cause oxygen depletion that will affect aquatic life. Because in the advanced countries, they are more concerned about their river system. So anything you're discharging into the river systems, they want to make sure that you clean them to an extent, because people downstream depend on those rivers for livelihood. But I know that the reverse is not the same in Nigeria, but then we'll get there. Rome was not built in a day. So these are the materials. So once again, I'll ask, have we all gotten the materials? Are we following? Any questions?
Well, we are following. Maybe I should raise my hand.
Okay, thank you.
If for me, I got the material. I got the material. It's only missing the user manual.
The user manual is not. The user manual is in one of the folder. Is incorporated in the swim folder. I've readjusted the material. So check the swim folder. You see the user manual, sir. Yeah, somebody said I have just 4 folders. Yes, I have the images of Abuja have been incorporated into the AutoCAD, and the user manual have been incorporated into the swim folder. That's an adjustment. That you're referring to the file in the cloud. Okay. Thank you. I've not gotten the material. Habib Alabi. Are you from C&A? Okay.
I can't categorically say because I'm viewing from my.
Okay, I've sent it.
Are we together?
I'm hearing you, sir.
All right, sir. So it's from my tablet. So it's on, when I get to my laptop that I'll check, because it's there that I have AutoCAD that can open it.
Okay. And somebody's complaining about the version. Please, if you couldn't open the AutoCAD file, that's no problem. I'll show you how to convert it to the bitmap or meta file. Call it meta file, but just a version of bitmap. Don't worry about that. Maybe AutoCAD is not a newer version, but I saved it in different versions: 2007, 2004, 2012. So definitely one of them will open in your AutoCAD. Provided you are using AutoCAD that is not older than 2004, you're going to get that. So now, let me present to us, my good friend did a small preparation on this. So let me just hold on a minute. Let me show something. Let me show something. It's coming up. While it's coming up, let me move on with some other things. I'm going to open a lot of files. Okay, things that opened. Okay, here we go. I think everyone can see it. So don't worry, I'm no more the technical secretary of NICE. That was when I prepared this material. So this is what an urban drainage system looks like. As I said earlier on, the first 1 hour of this lecture, I'm going to use to lay a foundation. So it can be a little bit boring for some of us. But this foundation is important because all of us are not water oriented. So I'll use the first 1 hour. We have 3 hours today. So the first 1 hour will be to give us the basics, the background again. And then after that,
good afternoon.
Yes, sir. I can hear you, sir. Yes.
Yeah, I've been struggling to connect, but now I'm able to connect. I haven't access to the material, like I sent the message yesterday.
What's your name, sir? Chat.
My name is Antonio Kiwelu.
Okay, Tony, just chat me on the chat box. I'll send it to you right away.
Okay.
Yeah, you got it. Thank you.
Thank you.
Okay. Yeah. Okay. So, agreement. Let me just Tony Ochiwelu. Okay. There you go. So looking at what you have on your screen, we are discussing urban drainage generally. So this is a typical drainage system. It's made up of the storm and the sewer system, the foul sewer and the storm system. I would like to create emphasize on this definition so that we can know it. So what you see here now, for instance, now is you see there's a separate system. There is a combined system, okay, and then there's combined, and then there's a modified system. Modified system is when you have a system that maybe when what we call dry weather flow. When it's white, dry weather flow means when there is no storm event. When there's no storm event, what is flowing in your sewer line is just the wastewater from the household, which is foul sewer. Then in some system, as soon as there is storm events, you go and lock the foul sewer line, and then only the storm will go, and the storm will not go to the treatment plant. Okay, when it's getting towards the treatment plant, there will be a diversion structure that will take it to combined sewer overflow tank. Some of us might not have seen some of these things physically because these are what they use in advanced countries to retain stormwater. Then the sediments will be separated from the clear water so that they will not empty it into the river so that the fish and the aquatic animals will not be affected. So that's what you have here. So what you have beside you here now is like a stream. I don't know if some of us are seeing it. So what you have here, 1 minute. So what you have here, this is like a stream. You can see my mouse. This is like a stream. So the whole idea is to take out the storm and the sewer, which is the wastewater, out of the catchments, out of the watershed. So for a combined system, you have these both pipes coming together and then being separated at the point of going to the treatment plant. So these are all storm structures, stormwater structures. So this is just a stormwater structure, for instance. Okay. Then these are some of the terms we'll be using for the stormwater. Let's start with stormwater now. For the stormwater, we're interested in the area, catchment area. We're interested in catchment area. So the catchment area for this course will be represented as ACS. So before I go there, just give me 1 minute. Let me get something that will further explain this to us. Okay. Just go on. So the storm have to do with catchment, have to do with area. Okay, what area is this runoff covering? That is what the one definition of it. So that is where you start making use of rainfall data when you're talking about storm. So when you get this from rainfall data, this rainfall data is a function of area. And when you get the area, you multiply by the velocity of flow, you get your Q. Because in both storm and sewer, we are interested in the Q, in the discharge. So it now depends on what discharge are you looking for. Is it the discharge for sewer line or the discharge for storm line? So just hold on, I just want to show us something. Just hold on. Okay. Let me give a description. I want to explain both of these systems so that let me lay that foundation, because it's very important for us to differentiate between sewer and storm, between sewer system and storm system. Very important that we differentiate. We understand it from a layman's point of view. So this is the general hydrologic process. The hydrologic process has to do with the precipitation. Okay, precipitation comes in, then transpiration goes back, takes some back, then some are intercepted, then some go as surface flow, others goes as infiltration. And when we talk about infiltration, we have surface deep infiltration and shallow infiltration, but infiltration is filtration. Some that infiltrates will go to the sewer water table where it will percolate and become groundwater. Then those that flow into the open water bodies, some will evaporate back. Then those that goes through the plants will evapotranspirate. So this is the hydrologic process. So after this hydrologic process, you now see the drainage system now. On your left, you have the sanitary sewer lines, sanitary wastewater, which are called foul sewer, or the sewer. It comes from household. Look at these houses, they are connected to the sanitary sewer line. So this is an example of a separate sewer system. You can see that it's collecting wastewater from houses, from septic tanks, from bedrooms, from toilets, from washing, from grey water, all that. It will now transport it directly into a headwork and then a wastewater treatment, a wastewater plant. Okay. Then for the separate system, still within the same catchment, the stormwater is coming from rooftops, from car parks, from industries, from gardens, and they all flow into the receiving water body. Has no business with wastewater treatment plants. It flows into the water body. Sometimes it has to be treated somewhere in between the line. It is optional. But in the combined system, you see wastewater plants coming from industries, coming from household, and then they flow together using the same pipe network, sewer network, until they come to here, what we call a control device. Then some will now flow down to the headwork, ending at the wastewater treatment plant to be treated, while the other ones will flow into the receiving water body. So in summary, this combined sewer is rare, but we're also going to treat it. It is rare because they use it in where you have space, problem of space, and in advanced country where you have the technology to be able to divert wastewater and to be able to monitor storm events and wet and dry water flow. Wet weather flow and dry water flow. You need to be able to differentiate which one is coming in and then how you control them. So you can see here, this is a sanitary sewer. It's coming from the kitchen, from the bedroom and everything. Then you have the storm sewer coming from the roof drain. This one is coming from the roof drain. So I think that's just what I want to draw here. So here you see that the wastewater is going to the wastewater treatment plant. We call them sewer pipes. They are usually made of PVC pipes. The minimum is 150 mm, and they can go as high as 600 mm or even 900 mm. But the storm drain or storm pipe can go from 600 mm to as high as 3 meters. You have 900, you have 1.2 mm, you have 1.5 mm. Most of them in Abuja are about 1.5, 1.8, 2 meters. But you hardly see a sewer line that is more than 450 or 600. And when you see 450, 600, that means it's getting towards the treatment plants. It's usually between 150, 300, 450. And it's made up of PVC pipe, normal PVC pipe. While storm drain is usually made up of concrete pipes or steel pipes. So that's another way to know the difference. So I can ask you, what is this on your right, on your left? On your left can be both. It can be sewer, it can be storm. But the one on your right is purely stormwater because it's open drain. You cannot convey a sewer and a foul sewer an open drain. It's not possible. The odor will cause environmental problem. So these are also shapes of both elements, both the sewer and the stormwater. I'm rushing these things because these are things we just to lay foundation. So for a network, for a system, you have the catchments and subcatchments. Then you have the nodes, the junction, the outlets, the flow divider. That's for the software. Then you have the link. The link, you have the conduit pipes. The link and the conduit pipe are the same thing. Then you have the pump. Then you have the rain gauge. You have the rainfall source. And then you have the outfall pour points. So these are the major elements of a drainage system, whether it's for sewer or it's for stormwater. So for a stormwater, there must be a rain gauge. There must be something, and that is what you get from your IDF curve. Then you must have outfall. In other words, where is the discharge point of the storm? Where is the storm entering? Is it a river system? Is it an open drain? Is it an infiltration basin? Is it a green area? Is it a swell? Or is it a detention pond? So that is where the storm water goes. Whereas for the sewer, you are talking about treatment plants. And some of us will have a natural treatment plant in our houses in the name of septic tank and sockaway pits. That's a mini treatment plant. So look at it from that perspective.
Yeah.
Then you have the link and the conduit pipes, which will convey those wastes, those flow from your houses, from your rooftop to the treatment plant or to the open drain. That is the pipe and the conduits. In some instances, there might be pump, but based on cost and energy consumption, it is rare to use pump in a sewer system, except in the treatment plants. Because what happens in the treatment plant is that most treatment plants, sewer is conveyed by gravity. So by the time it gets to the treatment plant, it is below ground level. So you might need a screw pump or any other kind of, or suction pump to pump it back from the base to the treatment level or to the primary sedimentation tank. So most treatment plants must have a pump because you must pump from the entrance, okay, from the grid chamber, how do I call it? The point of delivery where the water comes in. I'm trying to find the name. Is it water resources?
Lift station. Okay,
the station up to the primary tank, and then the process will continue. And then at the end of the day, you discharge it back to the open stream after treatment, after the passing through all the treatment processes. Then we have nodes and junction. I want you to see node and junction. Yeah, intake structure. That was the word I wanted to get. The intake structure, from the intake structure. Okay, so you have the node and the junction. The node and junction are just like your manhole. They are like your manhole, okay, which you see in some places. Then you have the outlets. The outlet could be the outlet from your house into the secondary pipe. Then from the secondary pipe, you move to the primary pipe. From the primary pipe is going to the treatment plant. Then you can also have flow dividers. Flow dividers, as I explained, sometimes you want to separate flow from storm and sewer for combined system. Then finally, all what we have saying must have a catchment. You must work based on a catchment area. There must be a default catchment, either in hectares or in square meters. Sometimes catchment can also be population equivalent, can also be computed based on population equivalent, especially if you're talking about sewer. Most times you just check the population equivalent, check what their water intake, the daily water requirements. They use it to catchmentalize your flow. Okay, so this is just a graphical illustration of what I just said now. In a storm event, there must be a rain system because it's rain. There must be a rain gauge. Then there must be catchments, which can be in hectares or in meters, in square meters. Then the water will come through into the conduit or the pipes, arrive at a junction, then goes through a divider if it's necessary, then goes to the outfall or goes to a temporary storage unit from where it is pumped through a combination of pump, regulator, back to the outfall. So what is the takeaway here? The final destination of storm is the outfall or the river system. And the final destination of your sewer is the water, is the treatment plant or your septic tank. So what are the steps you need to do when you are planning a drainage system? Number one is to visit the sites. You gather your survey information, which is very important. Your spot height, your levels and everything. Then you do what we call catchment discretization. I will explain. You need to know how many catchments, the size of the catchment, the slope of the catchment, the population equivalent of the catchment, or the population density, whichever one you want to use. So there are catchment information that you need. So you need to know the high point, the flow point, the streamlines, the location of the outfall, and the general gradation of the general undulation, the slope of the catchment. Then you need to understand the urban hydrology of that catchment. And that is where your rain data comes in. Okay? What happens in Lagos is different from what happened in Abuja, and it's different from what happened in Maiduguri. I know that Abuja is around 130 millimeter per hour, the maximum for 20-year rain. Lagos is around 140, 150. Bronu and up north, you can be getting like 80, 70, 90, and 100. Why this is important is that this is what will help you to get your Q, your discharge, based on the area. And then when you get your discharge, when you get your area, you get the intensity. If you multiply your intensity by the area, it will give you your Q. Okay, so let me just go to whiteboard and just say this. In our school days, we all know this formula. It comes in different variants, but they are the same thing. That your discharge Q is a function of your area, A, and your velocity. Some will write it this way: Q equal to CIA, where C is a constant. Is a constant. I don't know which one you are familiar with, but there's okay. Another version says this way: A times Q. That's this kind of Q. But here, this Q is different from the big Q, because this Q, the unit will be in meters per second. So I'm taking us back to the school days, okay? But this big Q is a meter cube. Take note, meter cube per second. Okay, because area only is already in watts, meter square. So this is a fundamental hydraulic equation. Anybody that's an engineer must know it. We did it in 309, Gene 309. It's a fundamental thing, and it's the foundation of storm design. Because our output is for us to get our pipe sizing. That is the whole grammar about the training. How do you size your drain to be able to accommodate that flow, be it storm flow or sewer flow? So the protocol and the process of getting your Q is important. Once you get your Q, problem is solved. Because with your Q and your slope and the return period, you go to many charts on the net, on internet, and you size your pipe. Then after sizing it, you detail it. That's all. Job is done. So the most important thing is to find the discharge, and that is why discharge is a function of the area. And now is a function of that constant. That constant is a function of many parameters. Is a function of the intensity of the rain. Is a function of the time of flow. what we call time of flow. It's also a function of the duration of the rain. Then finally, is a function of the return period. There's an intensity of rain that fell in Abuja recently. I told that people that rain is a 10-year flood because that estate is always flooded every 5 years. So as a water expert, I told them, look, this thing is going to be happening because the drain system in that area is not designed to accommodate more than a 10-year return period flood. So when a 10-year return period flood comes, it carries houses, it carries things. And it's going to, I told them, look, it can only get worse. I'm sorry, I'm not an agent of doom, but that is just the reality. Why? Because most people, when they do design, they undersize. They design, I'll still come to that. When you're doing your design, you have to ask questions. Are you designing against surcharge? Are you designing against flood? And even if you're designing for against flood, what kind of areas? And that is where you know the kind of return period to pick. 5 years, 10 years, 25 years, 50 years, 100 years. Nobody does 100 years, nobody does 50 years, because if you do those designs, your design will be so expensive. Your drain will be so big, so huge, that your clients will be questioning whether your head is correct. So most times you don't go, you use the standard to know if you're designing for residential area, for instance, you can use 5 years and 10 years, depending on it, depending on what your client wants. Okay, so these are the foundation here. So what you need to do now is to get your area, which is the catchment, the size of the catchment. Then I is your intensity. I is your intensity. In millimeter per hour. And you convert it to what? Meter cube per seconds. That's easy. No problem. We're all engineers. So that is what it is. So I think I've defined out, okay, C is a constant, A is this, okay, Q is discharge, okay? Now, this discharge can be used interchangeably. Most times you see people say flow. Good. Somebody say discharge. It's the same thing. Okay. Then if we are doing water, the one we are doing next week, the training we are doing next week, we call it water demand. We call it water demand. Okay. You can also call it wastewater demand. Yeah. Call it water demand, which is definitely the base demand anyway. All right. So let's go back to the presentation slide I was sharing with us. So these are the methods we're going to face. So for the urban drainage, for instance, what are the steps? Let's now emphasize on those steps now. Step one is you visit the site, as I said.
You seem to be muted.
He's back now.
Okay. So if you go to some, pardon me, please. So I said the degree of paving of an area influences the volume of runoff. If many of the areas are not paved, there will be a lot of infiltration. Like in the diagram on your left, you can see that because there's a lot of vegetation, 40% of the rainfall goes back as evapor in form of evapotranspiration. 25% goes into the ground as shallow infiltration. Another 25% goes into the groundwater as deep infiltration. So what do you have left? Only 10%. But if you go to the diagram on my right, which is a built-up area, which is a high density area in terms of the land use, you'll be seeing about 55% surface runoff. Only 10% infiltration. Why 10% infiltration? Because everywhere is paved. So that's why you see some of these areas in Abuja that are being flooded, Lokogoma, Lugbe. The reason is that people are building houses the more. So we are getting more paved area. People are using interlock. People are using macadam. People are using many types of things that we are not having that deep infiltration. So at the end of the day, you have massive surface runoff, which are not designed for. And that is why you are in this training. So that at the end of the day, your question will be to look at the layout and look at what will this thing be in the next 50 years, in the next 30 years. You project. When we do design, total design, we are always projecting our population for a lifespan of 30, 40, or 50 years based on the design criteria you are giving. So this is very important. If it's going to be high density area, then prepare for worst case scenario. If it's going to be low density area, okay, you can use your runoff coefficient as 0.3 or 0.4 or even 0.2. But if you're talking about high density areas, then I don't expect you to use anything less than 0.7. Okay. So look at some of this paving. You see that the runoff being contributed to this first figure is the highest. While the second one, there will be some level of infiltration.
We cannot see your screen.
Hello, can you share your screen?
Okay.
Yeah.
Thank you so much. Please, I move away from the whiteboard. Okay, thank you. So I'm saying that we all saw this. Hello.
Hello, we haven't seen this.
Okay.
We've not seen this.
Okay. Oh, sorry, please. I think I moved away from my normal view. So this is example of infiltration. I said if you're looking at the one on your right, on your left, you see that there are a lot of deep infiltration and shallow infiltration, and a lot of evapotranspiration. So the runoff is just 10%. Whereas on the one on your right, you'll be looking at only 30% evapotranspiration because they are not greens. And then because there's a lot of paving, you only see 5% deep infiltration, 10% shallow infiltration. So at the end of the day, you are having 0. This 55% now is equivalent to 0.5 coefficient of runoff. There are other factors to consider, but as a rule of thumb, your percentage runoff is directly proportional to your C. Remember, we talk about C. We talk about C here. Okay, this is your constant. So this constant is what we call coefficient of runoff or factor of safety. Is it called coefficient of runoff? And it's usually between 0.1 to 1. Yeah, 1 is almost impossible, but let's say 0.98. Let's say 0.98. Yeah. So every surface have different degree of coefficient of runoff. So I'm now saying, if you come to this catchment without doing any calculation, the coefficient of runoff of this catchment will be within the range of 0.5. While the coefficient of runoff of this catchment will be within the range of 0.1. So it means that the one that, if by the time you go back to this formula, CIA, you find out that you are getting more discharge with the one that has the highest coefficient of runoff. I have a lot of questions. I need you to share the screen. Here's the diagram reference. Okay. Okay, I got it. So, any questions so far? Those are ask questions on the chat box. Please, you are free to ask it now because there are so many of them. Please remember to mute yourself.
I brought it back.
Okay, so we continue.
I have a question.
Go ahead.
So in two of the diagram, you say one we can get a coefficient or runoff of 0.55 and the other one 0.3. Like 0.1. I don't know what is the basics behind.
Good. The basics is that this place is the run on your right. You have a higher degree of paving. You have a higher degree of paving is a high density area. Okay, so it means that this all the rainstorm that comes here, only 10% will go into shallow infiltration, only 15% will go into the groundwater, and 30% will go back into the cloud, into the atmosphere as evapotranspiration. So you now have 55% volume to deal with. So that 55 volume, by the time you consider the slope factor, it will be close to your coefficient of runoff. In the one on my left, because it's green area, so the water is able to percolate, infiltrate. About 50% of them infiltrate. Then another 40% evapotranspirate from the greens. So all you have left is now 10%. So 10% is now the quantity that will flow, that will constitute surface flow. And that is what you are designing for. Because your job as engineer is to make sure that this 10% is safely conveyed into the open water body.
Okay.
In this case, it's about 55%. So already you begin to see why the drain system, the one on my right, is going to be massive.
Yeah.
Okay. Thanks. And here I'm trying to show, to ask that these surfaces will contribute disproportional amount of surface runoff because some will infiltrate while others does not allow infiltration. Then, okay, so this is what I'm talking about. So catchment discretization is that you would ask yourself, what is the area of catchment or subcatchment? That's ACS, means area of catchment. Then you have what we call degree of paving. How paved is that area? Because what we are interested in paving is that it is only the rain from the paved area that contributes to runoff. When I mean paved, I'm talking about the impervious area. So when you see impervious, you see paved. It's the same thing. Impervious means something cannot penetrate. Then you talk about the surface slope. So these are the characteristics of catchment that you need to take into account. Then for sewer, we are not talking about population density. And here you're talking about the wastewater flow. If you're designing for a sewer system, you're talking about the wastewater flow. And then parasite water. Parasite water are like unaccounted water. Despite how sealed your sewer system is, there is still some level of infiltration water that comes into the sewer line. So when you get your base map, you digitize the network in this way so that you know which area is contributing to which area. So for instance, this place now is bounded by 4 drains. So which one is on the downstream? So that is the one that you pipe you use this area now to design this storm line. So in urban hydrology, you talk about the rain gauge, you talk about the temperature data and what have you. These ones are not important, but they are just some of those terms that you're going to face when you're talking about urban hydrology. That's the water cycle. The water cycle. Okay, this is, you can read, you can understand this. So this is talking about the software infiltration estimation. There are different methods you can consider. This example of the IDF curve, not too important. This will still come to this based on the degree of paving. Different areas have different hydrological soil group they belong to. You need hydrograph. If you didn't have an IDF, you can use hydrograph. which will also be used as your input parameter. Okay. These are some of the terms you'll be encountering. You'll be hearing things like rainfall, flood frequency analysis. You need to do your rainfall and flood frequency analysis. You do your original rainfall, flood frequency analysis. You do your rainfall runoff analysis. Then, as I said earlier on, based on still on urban hydrology, there's what we call duration of rain or time of concentration. But let me just explain to you what it means in a layman's language. The flood, the rainfall that contributes to flood is that rain that is equal to the time of concentration. In other words, when there is a storm event from, say, let me draw it here. Eraser. Okay, draw. Let's say this is a catchment. Okay. These are catchments. There's another catchment here. There's another one here. And all of them are emptying. All of them are emptying into this sewer line. And then this is the outfall. Sorry. This is the outfall here. This is the outfall. And this outfall means there must be a river here flowing. Okay. So this is the outfall. Normally you use riprap here so that to avoid the scoring. We do some scoring protection there. So now, what we are saying when we talk about time of concentration is that if there's a drop of rain here, how long will it take this rain to appear here? That's what we call time of concentration. If it is more than 10 minutes, the one that contributes to much, if the rain falls for 10 minutes, then this distance must not be more than 10 minutes for it to contribute maximum. This is a difficult concept for some of us who are not into the water sector, but just stay with me. So that's why when you want to read your IDF curve, you read your IDF from 10 to 15 minutes, because it is expected that the rain that will contribute to flooding must not be more than 10 to 15 minutes for it to flow from here to here. If it's taking 30 minutes, that rain will not contribute to flood. If it's taking 1 hour, forget it. You are safe. So the one that will contribute to flooding is that one that will take the same time that the rain is falling. In other words, if the rain is going to fall for 10 minutes, let's say, then it means that when it hits the ground here, it will take 10 minutes to flow to the outfall. So that is what we call time of concentration. So in design, if the rain is taking longer than 10 minutes to approach this outfall, we assume 10 minutes. If you go to your frequency flood this thing, you will notice that in the horizontal axis, okay, sorry. If you come to your IDF curve, which is the rainfall data, you notice that the shorter the rain, the higher the intensity. The shorter the rain, the higher. In German standard, they use not more than 15 minutes maximum. And let's say it's a 2-year rain, a frequency with 2 years. The 2 here is about 120. And the 10 minutes is about 140. You could see that the shorter, the more intensity it is. And let me just tell us this. In weather prediction, in all this CNN prediction we see on the news, once they measure the intensity of rain in the first 1 hour, they will tell you whether there will be flooding or not. That is the secret. If I measure the intensity of rain in the first 30 minutes, and it's giving me like 100 mm, then I'll blow alarm. That is how it is done. Because by the time you now do your unit hydrograph with that tense intensity, it will be giving you discharge. When you multiply by the area, if you multiply 100 mm by, say, 1,000 hectares, and the volume is going to come to one particular channel, then you know that that channel is going to flood. So that's the secret. So all this I'm saying is trying to explain to you the meaning of time of concentration, because it's important that you know time of concentration or time of flow. They can be used interchangeably. Concentration, time of concentration, or flow time. Well, time of flow is it's all grammar. Flow time. And here I've said usually use what? 10 minutes. Worst case scenario, 15 minutes. But the shorter the better. Okay. So let's go back to our short foundation. So the next thing is frequency of rain or return period. Frequency of rain. We are all engineers. Frequency means how often. What is a second? How often does it happen? That's the frequency. How often does it happen? Then it is the reverse of return period. So in mathematical terms, we usually say that frequency of a rain is the inverse of the return period. Is written as T. Now, let me explain. If, like, for instance, let me give one example. I was in Germany when this happened, but I took cognizance of it. The 2012 flood that happened, even though we've tried to explain it, that it's because of Lagdo Dam, we don't have a check dam, blah, blah, blah. But I know that that was a 50-year flood. Why? Because when they were interviewing some people in Bayelsa, some old people, they said the last time they experienced something like this is 50 years ago. And I told us about what is happening in the Trademore area in Abuja, that those people have seen that they have a return period. They are suffering from any flood that has a return period of 5 to 10 years. Because in the last couple of years, we've seen every two years, every 3 years, they have this kind of scenario. So what is that rain? It is that highest rain that's expected in a layman's language. Let me explain it so we understand it. What it means is that, what is that maximum rain that will fall once in at least a certain number of years? So when I say this is a 5-year flood or 5-year rain, whatever terminology you use, when I say a 5-year storm event, that's the most technical event, technical word, a 5-year storm. What this thing means is that this rain will happen at least once every 5 years. It means to happen at least once in 5 years. That's what it means. If I say 25-year storm events, or 25-year flood, or 25-year rain, or 25-year return period, whatever suffix I use, it means the same thing. It means that I expect this type volume of rain, I expect this intensity of rain, I expect this magnitude of rain to hit the ground at least once in 25 years. That's what it means. It means I expect it to hit the ground at least once in 25 years. 1 minute, please. One of us is trying to join. But okay, so that's what it means. So in a layman's language, that is what it means. It means at least in every 5 years, 25 years, I expect that rain to fall at least once. So it means that when I see that rain fall, I will know that definitely that rain is anticipated. Okay. Then the IDF curve, the IDF, intensity, duration, frequency. So you can see that the IDF curve have done you well by combining these three factors. So all you need to do is just to pick your I, multiply by the A, consider the C, you get your discharge. With your discharge, you go to your chart, you design your pipe, and that will be it. So for instance, now this is it now, this is the IDF. Okay, the IDF have captured, here you see the return period. So if you are doing a 1 year, 2 years, 5 years, 10 years, 25 years, 50 years, 100 years, this thing normally comes into play when you are talking about dams. When you are designing dams, when you design your dams, you do your feasibility study, then you know the kind of rain that falls in that area. And then you know how many years do you expect that dam can be overtoppled. If you are designing for 25 years, it means what you are saying is that this dam cannot be toppled, can only be toppled, once in 25 years. It might not be toppled, but that is a design criteria. So when you say 50 years, it means that if any flood that is below 25 years cannot topple this dam. If you say 50 years, it means any flood that is below 50 years cannot topple this flood. What? But if a 100-year flood comes to topple the dam, if you design for 10 years, if a flood of 25 years comes, the dam will overflow. So that is what it means. Now, in urban drainage design, when you are designing for some areas, you use 2 years. Some areas you use 5 years. Some areas you use 10 years. I don't see you going beyond 10 years. There's a table for that. I will still come to that. You design based on if it's a rural area, you use 1 year, 2 years. If it's a hydro area in the US where we have high insurance, for instance, you use 5 years. Because if there's a flood event, the insurance company will pay hell. So when you're doing design in such area, like in a central area now where you have banks in Abuja, if you are doing the design for central area, you're going to use like 10 years. Meaning that you are, or even 25 years, but 25 years will be too much because it will be very expensive. It will be massive. And government might not approve it. Okay. So I think we're making progress. Now, this is what I'm just trying to say. The return period is the inverse of the frequency. So it means that if there's a 12.5% chance that the storm of a certain magnitude will occur, the return period for that storm will be what? 8 years. So the higher the return, the higher the frequency, the lower the return period. We all know our inverse. So what this thing means is that if I say I'm designing for an 8-year flood, it means the probability that that flood will occur is 12.5%. If it is 1%, if it is 0.1% or so, it means that flood can only occur in 100 years, and so on and so forth. We can do the mathematics anyway. So all these ones are not important. You can read this one, you can understand them, about urban hydraulics, about flow. So let me just explain this in a layman's language, what this thing means. What this thing means is that there are many flow routing methods. Some considers what they call the invariant equation. It means that flow is moving in 3 dimensions. It's flowing in 1 dimension. As it's flowing, it has magnitude, it has momentum, then it's having turbulence, it's also changing direction, and it's also having impact with the body, with the surface. Let's not go there, but this is academic work, but that's just the layman's language. It means that the energy of a system, when water is flowing, it has 3-dimensional flow. is flowing within itself, is flowing in one direction, is also turning, is also having momentum. As it's moving, it's turning. So it has like three forces. It has a kinematic wave, it has a diffusion wave, it has the normal energy and slope terms. All these ones are not important. They are just talking about kinetic flows and flow routing. Okay, flooding and ponding. You can read it, you understand it. All right, so that is that. So any questions so far? I'm trying to find my file. Okay. So back to where I was before I venture into that slide. I was trying to explain the terms we'll be using in the course of this work. ASC will represent catchment area of a given point. Then ACP will represent sum of all paved surfaces, including rooftops. Then ACNP will represent sum of all unpaved surfaces of a catchment. Then this gamma will represent degree of paving. Okay, here he said in international literature, the term impermeable area or impervious area are often used as synonyms for paved areas. Respectively, unpaved areas are referred to as permeable or pervious areas. So those words can be used interchangeably. Now, how does runoff generate? We are still talking about general urban hydraulics. When there's a rain event, for instance, many things happen. The first thing that happens is what we call wetting. After wetting, some will go as infiltration. Some will go as drift. Some will go back as evapotranspiration. I think I've explained these things. Then some will go as deep storage or deep infiltration. Only a small number will flow surface as surface runoff. So that is why it is not every area that is contributing to runoff. Some areas will infiltrate. So that's what this is talking about. Constant rain intensity does not generate constant runoff. Maximum runoff occur only after initial losses. And that is what wetting, depression, storage are covered. Higher degree of paving leads to less infiltration. And that translates to higher runoff. Wetting losses, maximum depression, storage are almost constant values for a given surface area. The higher the rain volume, the higher is the runoff percentage of runoff. Of course, this is self-explanatory. The higher the rain volume, the higher the runoff. So that's why if the rain volume from your IDF curve is very high for 20 or 10 years rain, that would automatically translate to a high percentage runoff. So calculating the runoff in design procedure is based on block runoff. In other words, we use a block model to assume runoff. And that block model is that the discharge runoff, this QR means discharge of the runoff, is a function of the rain intensity R, which is a sub-function of the duration D and the frequency N. So it means when you are choosing your intensity, rain intensity, you must consider the duration and the frequency. Then you multiply it by your area of catchment and multiply it by that coefficient. So this formula you are seeing here is the same thing as your CIA, which we are taught in our school in Nigeria based on our NUC curriculum. They use CIA, coefficient, intensity, and area. But here in the German DVR, I'm a member of this body anyway, by the way, the only one that is responsible for the coding and standard of German engineers. So their own is the same thing. This RODN is one word, and that is your I in our own. A is the same, only that they are telling you ACS now means it is the catchments and subcatchments. So most times why we put ACS is that you might have a catchment emptying into another catchment. You might have Wuse 2, those in Abuja, sorry. You might have Wuse 2, Wuse zone 2, emptying into Wuse zone 3 before it now goes to the stormwater, to the open channel. So that means that Wuse 2 become a sub-catchment of the whole catchment, which is 2 of them. I will still explain this when we come to design, but just have the whole concept. So you can see that this formula is not different from our CIA. For a given surface, the ratio between precipitation and runoff depends on the rain intensity, and it varies over time. Runoff coefficient can be given only for certain conditions. We need different values to solve specific problems. Peak runoff, mean runoff, and the rest of them. Okay. What is, we have runoff. I've been talking about runoff coefficient and I've been talking about peak runoff. When you hear the word peak, it simply means the highest. It means the worst case scenario. It means the optimized, the upscaled factor, the one that you use for your design, the one that concerns the peak period. In water reticulation design, we normally design our design based on peak values. In other words, those times when water consumption is highest. So the same thing applies here. You do your design based on when the runoff is at the peak. Okay. Okay. And that's what we use for our sewer sizing. These are not important. Now, when you have different bodies, different catchments with different runoff coefficients, you now use what we call the mean weighted average. The mean weighted average, you know, there's a difference between normal average and mean weighted average. When we talk about mean weighted average, we are referring to the average that takes into cognizance the volume of each area. Now, I might not go too deep into this, but the best average method of weighing systems is by using the weight mean average. So for instance, now, let me explain. Let me explain with the whiteboard. If I come to, let's say, let me erase. Okay. No. Which I can do. Okay. Let me undo. When we come to the catchment, for instance, if the runoff coefficient, in other words, this place is highly paved, is 0.7 here, and the area here is 50 hectares. And I come here, the runoff coefficient here is 0.4 because the place is just so. It's not too paved, it's not less paved. And the catchment is 25 hectares. If I now want to calculate the weighted runoff peak, the average coefficient here, the weighted average, let me call it weighted average, WA. Some people say mean weighted average. It means I will consider 0.7 multiplied by 50. Watch me, just stay with me, plus 0.4 times 25, all divided by, let me use a line. It will be all divided by the total area. In this case, 75, or 50 plus 25. If I calculate this now, that is what we call mean weighted average. If you look at it, if you have this area, but it's 0.7, and you have this area, there's 0.7. If I calculate the mean weighted average, let me get you the answer, because this is very instrumental, so that when you have different catchments with different areas, you'll be able to know, take their mean weighted average. So this is 0.7 multiplied by 50, to give me 35, okay? 0.4 multiplied by 20 to give me 10. So the denominator here is 40. The numerator, sorry, divided by 75. 45, sorry, this is 45. 45 divided by 75. The answer is 0.6. 0.6. But if I ask you to find the average of these two coefficients, these two mean coefficients, let me see what I'll get. I'll get 0.7 plus 0.4 divided by 2. I'm getting 0.55. So the question is, which one is more accurate? I can tell you 0.6 is more accurate because it's taking into account the weight of each catchment. So this is both of them are close, but if you have different catchments, some that are 0.1 and their hectare are so big, you see that it will be drawing the mean towards itself. So that is what I want us to understand from there. So we move. So this is how to calculate the mean weighted average. That's just all I've just said here now. He said when the drainage system is planned for future development, the percentage of each surface type is unknown. The expected distribution of surface types can be estimated based on the land use. Even in water reticulation systems, we use land use. That's why land use is so important. And we should stop abusing it in places like Abuja. When we plan our cities, we have a defined low density area, medium density area, high density area. The idea of this is that high density area might have 4 floors, 10 floors. The low density area might be bungalows. Then the medium density area might be just be, let's say, 3 floors, 4 floors. So this is important for infrastructure planning. If you get them wrong, if you design for a low density area, if you design for a high density area, you're going to have a lot of issues. Then if you design the low density area you use the design for high density area, you're going to incur a lot of costs. So it's always good for you to ask to know what is the land use of an area. What was planned there? How many families per hectare? That will go a long way in helping you. Okay, so we're moving close to starting our design. Then I told us something about peak runoff coefficients, depending on the degree of paving. So here, the peak runoff, if you watch here, you see that roof is about between 0.8 and 1. That's the peak runoff. Gravel is about 0.7. Green roof is between 0.3 and 0.5. Asphalt is about 0.9 because asphalt is absolutely impervious or not permeable, impermeable. Water cannot penetrate asphalt. So virtually all the water, that's why the runoff is almost close to 1. It is never 1 anyway. Then, so these are all the, so you look at unpaved surfaces. Unpaved surfaces that can produce runoff. If it's a flat surface, it will be between 0.01 and 1. If it's very steep, it will be a bit high. 0.1 to 0.3. Okay. So now the peak runoff also is not only a function of the paving, it's also a function of the slope. The more slopey an area is, the more runoff it will contribute. So if it has a steep slope, it will contribute more runoff. So for the design storm, we use a frequency of 0.5. 0.5, you say 1 over 0.5, that will be 2 years. So the return period of 0.5 means 2 years. What it means is that every 2 years, the probability of this rain occurring is half, or 0.5. It means it will occur once every year. And the rainfall duration must be greater than 15 minutes. So that is that. So this thing you might not quite understand it, but it's just telling you, pardon me, is in German, but it's just telling you that if a slope is small, then the runoff will not be much. If it's small, the more slopey a place is, the more runoff it will contribute. Okay, so we have discussed all this. Yeah, I've retreated this. Okay, now we've talked about the stormwater. So this is all about stormwater. Your A, your intensity. This, look at it here. Look at the formula here again. ACI. So when we come to separate sewer or sanitary sewer or foul sewer, we are no more talking about IDF, rainfall intensity. No, we have no business with it. Rather, now we're talking about wastewater flow. And we're talking about dry weather flow. We're talking about dry weather flow, we're talking about wastewater flow, and then we're talking about some factors, some few small water that will also flow into the network. So, but for stormwater, we'll just say that the separate stormwater system is just the QR, which is the runoff discharge, which we just explained now. Then if you're not doing a combined system, you will now do DQ, which is the wet water flow plus the storm water flow. I've explained all this one before. I've explained it in the other chart. So how do we describe some of our parameters? The first parameter we have in urban drainage is the duration. The rainfall must have duration, and the duration is calculated in minutes. It can also be in hours, but because it's always less than 1 hour, minutes is preferable. Then we have the depth, the height. What is the depth of the rain? Is in millimeter. That's when we say rain intensity, we say millimeter per hour. It means if you measure it in a gauge, it will be as high as this. The next one is, sorry, one of us want to come in. Just give me a few minutes. The next one is the frequency, the intensity, the frequency. Okay, so in the time past, they use sorry for that interruption. In the time past, the formula that is used for rain intensity is this formula, which will come out as liters per seconds per hectare. So you just multiply the intensity by 167. So it's a conversion factor. I've not tried it, but no, it might work. But I will show you the other way to do the conversion. So this is like a conversion factor to convert it automatically from millimeter per hour to liters per seconds per hectare. Then we have this classification of rain. Okay, it's just like a guide. If it's less than 7, the equivalent of it when you do the conversion, it will be 650. It will cover about 650 hectares per annum. Then you have the moderate rain, you have the heavy rain. So when it is this is what it's contributing. Equivalent is contributing in terms of land mass. Then this is the rainfall data. This is the one they have in Germany. It's in millimeter per hour. Hours is the other way around. And this is the duration, and then this ones means, so this first one is for 1 year, 2 years, 5 years, 10 years time period. So how do I explain this to us now? The old formula they use captures the intensity of the rain, the duration, and the frequency. So these are the 3 factors that makes up the rainfall equation. Okay, so if by the time you normalize this one, it will give you something like this. And what is this? This one is just telling you the rainfall intensity at a certain duration, at a certain frequency, is a function of the intensity multiplied by the time factor. We call this time factor just a safety factor. So normally in German, which is just close to what we have in Nigeria, the duration is usually fixed at 15 minutes. So you use the 15 minutes rain. as your guide. Then the frequency is maybe for 1 year for a normal drain. So in Germany, it's usually between 90 and 30 liters per hectare. Okay, then, and this frequency, this holds when the frequency is between less than 4 and more than 0.05. And the duration is less than 150 minutes. So we've talked about this. When there's infiltration, we have infiltration, this, and finally we have runoff. That's why it's in red. So all these ones are not captured, but this one is the one you're going to design for. So the peak runoff, which is a dimensionless constant, is the stormwater over the rain intensity. I've discussed this before. So this is a typical model of an impervious area and a house connection. So you can see that this is your main sewer. This line is not your main sewer. And then these ones are just connections. Yeah, I prefer to call them the temporary sewer lines. Temporary and tertiary. These are the tertiary. Then this one going straight is the primary sewer line. So you can see house connections. These houses are connected, so they discharge their waste into the main sewer line. From there, the main sewer line goes to the wastewater treatment plant for the foul sewer, for the sewage, while for the stormwater, it goes to the open body. So this is the formula we had before, but this formula, some things have been removed from these formulas. Okay, like this time of concentration and this location, the frequency is this. So they have now removed some of these things and just come up with a simpler one. And that simpler one is simply saying that arrow CIA. That's just what it means. So these two have been combined to represent catchment area factor. While these three have been combined to represent peak runoff coefficient. Now let's do a small example. Let's do a small example. This is a catchment of 100 hectares. Out of these 100 hectares, the areas that are paved, the areas that are impervious, the areas that will not allow water to fall in are 45 hectares. And the area has a population of 10,000 capita. And the water consumption is about 150 liters per capita per day. That's WHO standard. And infiltration water, which is unaccounted water, is about 5 liters per second. And the time of flow, T, is about 30 minutes. So how do you solve it? So to solve it is you calculate the wastewater flow. The wastewater flow can be calculated from the water consumption. That is the way to calculate wastewater flow, because it's expected that what goes in must go out. It is expected that if water board will give you 10 cubic meters of water, you're expected to produce back 50 cubic meters of water, because that is what goes in, what comes out. So when you do this, you get the answer. It's not necessary. We'll still come to the chart. So this is what I was trying to say in the morning. Catchments, from catchment to CS tank. From CS tank, you treat it, you discharge some, and those you cannot discharge, you go to the treatment plant. So we explained this to before. This is a stormwater sewer. It's going to the river. Whereas this is a sanitary sewer. It's going to the water. Wastewater treatment plant. Then for the combined system, these are separate systems. And when you now combine them, it means both the wastewater and the stormwater will flow in the same pipe, but not the same time. Because when there's no storm event, it will be wastewater flow. And when there's storm event, it will become a high water flow, dry water flow. When there's no storm event, it's a dry water flow. So you can see in a combined system, when it comes to this place, it will go into what we call combined stormwater overflow. Then from the fine water overflow, the highly concentrated type will go to treatment plant for treatment, while the other one will go will spill through the spillway. So these are the difference between a combined system and a separate system. But we're not interested. Someone want to say something?
Yeah. Can I ask you a question, please?
Is still my audio? Is my audio still falling? Go ahead, sir.
It's a bit steady now.
Okay, thank you. Okay, please, when it does, let me know. I think it's coming from the computer port.
Okay.
Okay, so we can read this, gentlemen. One thing I promise us is that I will not read what we can read and understand. I'll be hitting the critical things. So we can. So these are the disadvantage and advantage of a modified system and a single system. You will understand that one when you read it, please. So I'm thinking of starting rational method today because I don't know whether this lecture is boring. It's a theory. I'm laying a foundation. So I don't know whether we're getting it. I don't know whether we should observe a few minutes break, maybe 5 minutes, so I can take something. Before I go, I still have 2 more slides.
Can I quickly ask you a question, please?
Yeah, go ahead, sir.
Okay, so thank you. The other time you were talking about separate sewer system and combined system.
Yes.
And you meant something like in a particular system, there will be like a junction where somebody will go and switch something off or on when there is stormwater.
Yeah, storm event. Yeah.
So how does that work? Now at those time of rain, the foul, the effluent from houses, where do they go at those points?
Thank you. Now this is what they do. When there is no storm event, what you have is dry weather flow. Take note of that. Dry weather flow. That dry weather flow, what they do is that the system is designed like a throttle. I will get a picture of it later and show you. When you design the pipe, it will have like a 2 segments. The down segment will be like a PVC pipe, open, a PVC pipe that you cut, open. Then the bigger one will now come. So what they do basically is that when there is no storm event, there's no rainfall, they will open the gates, the valve to the treatment plant. Water will be flowing. Once storm event starts, the divider, there's somebody manning this thing, gentlemen. So it's an advanced society. So they will turn the discharge and it will be going to treatment plant. Now, your question is very important because at that point, does it mean there is no sewer coming from houses? There are, but at that point, they are so negligible compared to the storm that is coming. That's number 1. Then number 2, what they also do is that the combined sewer overflow will be separated into 2 segments. That's how I will look for the picture. Is like a bottom discharge. It will have a bottom discharge. Okay. It's like when you have when you are desilting a dam, when there's a bottom outlet in a dam made of steel. Okay. If you open the bottom outlet, you'll be seeing sediment. There'll be some kind of thick sediment that are coming out. But if you open the spillway, you almost be seeing clear water. So I want you to put in your imagination, that's what it looks like. That's what it looks like. It's like if there is a contaminated jug, puncture the bottom. The effluent coming out of the bottom is not the same one that is overflowing. I'll look for the picture and I'll demonstrate this, please. But it's a very good question because one will maybe imagine how do you combine sheet in quote, sheet water and storm water. I mean, it doesn't make sense, but they have special system. And meanwhile, these things are rare. They are only done in some high-brow areas in New York, in Silicon Valley, this high place where they have problem of space. So you don't have space to start building separate systems, but separate system is the ideal. I think 90-95% of the systems we have are separate systems. Storm system is different, sewer system is different. Even in our infrastructure design, we normally lay the sewer line bottommost. Then we now lay our storm line on top, and then our water line above, and then communication and all that ones takes priority. Okay. Any other question, please? While I attempt to bring in a chart that will buttress that point. I doubt if I'll see it. No, it's not here. It's okay. I think in the course of the lesson, I'll bring it up. So that is the end of that. So that's the end of what did we just finish now? We finished hydrology. I think we've done hydraulics already. Let me see.
Did we?
Hydraulics. Oh no, we've not done hydraulics. So let me quickly rush through hydraulic. Hydraulic, there's no big deal. Hydraulics. Hydraulics. These are some of the components you meet in a sewer system. Gully inlets. What are the jobs they do? What are they for? What are their widths? All these things, if you read them, you understand them. This is what a gully inlet looks like. Then we have the pipes. We have the closed pipe. We have sedum. We have ditches. They flow by gravity. The sedum flow by force pipes. Let me just say this: 95% or 100%, even 100% of storm systems are flow by gravity. Most of them are flow by gravity. The wastewater from your house, when you leave your house, enters the sewer line, it flows by gravity until it gets to the wastewater treatment plants. The same thing happens to your storm line, the one we call gutter in local parlance. If it's not flowing by gravity, there will be a problem. There will be sediment deposition and cost of energy will be so high. Okay. So in a cross-section of a profile, we consider some values: amount of wastewater flow, the slope of the sewer must be known, then the variation must be known. This variation helps you in what we call in pipe sizing. We'll still come to that, so that you know your full flow and half flow. We'll still come to that, just relax. Then you have the depth of sewer. Then you have other factors. All these things, believe me, gentlemen, if you read them, you understand them. Okay. Different cross-section. The one we know that is most common is the circular profile, but there are other ones, some egg-shape, and we have egg-shape, and we have mouth-shape profile. I just wonder what that one means. Okay. Hold on, some people are on the waiting room. Just for them. Keep telling me there are people waiting in the waiting room. Okay. All right, I think they've joined. So I will stop by 5. 2 hours. I think this will take us 1 hour, but it's taking us 2 hours for the foundation for this course. So all these things, I think we'll read them just for our own knowledge. Read them. They are self-explanatory. Don't need to emphasize more on them. I mean, verify clay, concrete, bleak, plastic. What are the advantage? What are the disadvantage? What are the sizes? What are the investment costs? I mean, no need for all those ones. Okay, if you're laying your sewer network, there are some recommendations. Number 1, follow the shortest possible way to save costs and to conserve your slope. Say with the slope of the streets, but suitable slope to avoid deposition. Follow the best slope so that sediment will not deposit. For sewer, the sewer is very dangerous. Any mistake you do in sewer line, there will be blockage, because sewer carries things like debris, tissue papers, and what have you. They carry a lot of suspended solid matters. They contain a lot of dissolved solid matters. So you must pay cognizance of the sloping so that they don't go and deposit. And by the way, the minimum velocity anticipated in a sewer network is 0.3 meters per second. Please, you can write it down. This is very important. Minimum velocity of flow. The velocity must not be less than 0.3. And the maximum is about 3. So between 0.3 and 3, you don't have to have a high velocity on C1 network. You don't have to have a low velocity. High velocity will lead to what we call supercritical flow. And supercritical flow has a way of affecting the pipe, number one, in addition to other effects. And it will erode the pipe with time.
3 meters per second is the minimum.
Is the minimum, and 3 meters per second is the maximum. Is a range.
No, you say 3 is the minimum.
No, 0.3 is the minimum.
Okay, yes.
0.3 is the minimum.
Yes, yeah.
Okay. Then 3 is the maximum.
Yes.
Based on German standard.
Anyway. So just scouring.
Scouring and other things. Yeah. It's more pronounced in potable water. But in the sewer line, take cognizance of the minimum flow. If the minimum flow is less, then there is a risk of sediment deposition.
Sedimentation, yes. And
that will lead to blockage.
Yes.
And then to ensure that this parameter is met, take cognizance of the sloping. The sloping must be right. And that is why, like in Whooper, in Abuja, the difference between the highest points and the treatment plant in Whooper is 12 meters. It's 12 meters. That means by the time we have a 12 meter, and then when it gets them, they will now pump it using an Archimedes screw, which is the commonest one they use because of low cost and volume, and to be able to carry. Let me not go there. There are many things that makes it more important than using other types of pump. Then in urban areas, pipe every street. Yeah, of course, I mean, you must convey all the wastewater out. Then pipe sections of similar lengths with less than 100 mm. What this thing means is that sometimes if you design your pipe and you got 90, 80, just summarize it to 100. Okay? That is for the tertiary pipe. For the secondary pipe, it should not be less than 150 mm. Then diameter of pipe only at manhole. Change diameter of pipe only at manhole. When we talk about manhole has some uses. Either your pipe is changing direction, is changing size, or is changing elevation. That is the function of, or for maintenance. Those are the 4 functions of manhole. Anywhere there's a change in direction, change in slope, change in height, you are meant to introduce a manhole at that point. In fact, if you are changing your pipe in a C1 network, you are supposed to introduce a manhole there. Okay, that is that. So here it says minimum diameter, it says sanitary sewer, DN 250. Ignore this. 150 is the new standard. Okay, this is when it's a minimum simply means the average. Then for stormwater and combined, it's about 300. In other words, if you are laying a storm line, you cannot use pipe that is less than 300 mm. Then if you are laying a sanitary sewer, you cannot use a pipe that is less than 150 mm or 6 inches. So if you go to any estate design or any district design and you see them laying a pipe that is less than 6 inches, know that they are doing the wrong thing. Even if the flow is, even if 100 mm can take the flow, the standard says that the minimum should be what? 150. Okay. These are things we can read.
Sorry.
Go ahead, sir.
You mentioned when you introduce manhole, when change of size of pipe and slope.
Yes. Direction.
Change of size. Direction.
And maintenance.
And maintenance. Okay. What of maximum length allowable that you can fly?
60 to 120. Between 60 and 120.
60 to 120.
It's in a manual. You will see it very soon. Between 60, there is a range, sir. Between 60 and 120, you are meant to introduce a manhole in a storm sewer. Between
that's
60
for every 120. Yeah, for every 120, there must be a manhole.
Between 60 and 120, not more than
there
120.
Must be.
There must be for maintenance and for all these parameters.
What about some designs where?
That's for storm. This is 120. What of in sewer?
For sewer, the same for sewer, but It depends on the manhole. Depends. I think for it is basically for storm. For sewer, I'm not too sure what it is, but you can use the same for storm. The reason is being that the guy that needs maintenance moves is storm. For the sewer, is mainly discharge points and inspection chambers.
I want to ask a question.
If you now have less than 60 meters, is something wrong with it, or is it acceptable?
No, if there is a need for it, maybe there's a change in slope. If they are the first three, to satisfy the first three, which is change in slope, change in direction, change in level.
Okay.
Direction, level, pipe size.
Okay.
I have a question.
Now, sorry, sir, 1 minute. The idea of pipe size is that for blockage, so if there's blockage, you know the access points to maintain it. Then change in level means also, in fact, all of them are tied to blockage. So the major criteria for the design is to avoid blockage. So all these manhole we are expecting, we're introducing, is to avoid blockage.
Okay.
The next engineer can ask this question. Hello, sir. You have a question, Engineer Akawe?
Engineer, yes.
Okay.
There's some designs where at the point of manhole you introduce pumps.
Okay. Why?
I have seen. Sir?
Why pumps?
Well,
in what design? Is it storm or sewer? Or
storm.
That means there might be change. Maybe there is a negative change in elevation. A negative change in elevation.
Yes.
But you should, as an engineer, don't design that, sir.
Well, I didn't design, but I saw it in one of the state government works.
It's wrong, sir. There must be, unless there are no other options, sir. If there's no other option, we should explore it.
It was on a groundwork, so it was done maybe just to
push the water. No. The idea is to, we use slope very well. As I said, we want flow to be by gravity.
Well, if we cannot get the invert level, I think they had a problem.
Yeah.
Getting the invert level. The thing was going too deep.
It's okay. I understand now. That's why I said if we don't have any other option, okay.
Yes.
We can take it.
Yeah. Yes.
Okay.
Sorry.
Go ahead, sir.
Is there a minimum depth that you can now go when you now say, okay, you can get appropriate invert level?
No.
Can that be an excuse?
That's the point. Cost.
Yes.
Cost of laying.
Cost. Yeah.
Cost.
Yes.
Like here on the screen here, you see that in Germany, in all these countries where they have issue of freezing, they make sure they lay their pipes at minimum of 2 meters, because at the peak of winter, during January, early February, up to 1 meter of the ground can be frozen. And if the wastewater inside freezes,
if it meets, it's a big problem.
So all these things are something we can adapt based on our unique scenario.
Environment, yes.
But me, I know that anything from 1.2 in our side, depending on whether it's crossing express, those things are in our highway design manual in volume 1, volume 2. It's not within the scope. It's also still within the scope of this training. But between 600 mm and 1.2. 600 mm and 1.2 based on highway design manual. But the going towards the upper end is not a function of the traffic and the overburden. So from your question, there might not be any minimum depth, but there's a depth that is cost ineffective. Even there's a depth that is not feasible. Are we communicating?
You're right.
There are some level that the risk factor is too high. Okay, so let's continue because I want to stop. It's already 5 because I want us to go into rational method today. So I think some of these things I'm not going to say much about them, but if you read them, you explain them, you will you understand them. okay, look at what I'm saying now from manhole. It talks about 70 to 100 meters. In another place, in another standard, it talks about 60 to 100. So these things are just small changes. Okay. Okay, say for pipe diameters, is this, depending on the pipe size. So this is what you consider for your manhole spacing. Then these ones are just self-explanatory. You go through them, you'll definitely understand them. So all from here now is just giving you some terms, definition of terms, just for you to understand. Okay, engineer that asked me about that question, about what's the feasibility of combining both flows. I think what they do is something like this, but it's not completely this. But this is what it looks like, but it's bigger in size. So during dry weather flow, your sewage will flow through this orifice. Then during stormwater, the whole thing is filled up. While this one still continues to flow, but a bit diluted. So these are just what we can.
Okay. Sorry, I want to quickly ask something.
Okay.
Can I go ahead?
Go ahead, sir.
Okay. I think I saw something that looks like around this sector B in Abuja.
Okay.
I saw something that looks like as if a sewer, a foul sewer,
okay,
on its pipe. They now diverted a storm water there. As if maybe it's supposed to be used to flush or something. I don't know, maybe to aid the flow or something. Is that allowable?
Are you sure that wasn't an error? Was that thing done by default? Because there have been instances where people go and push sewer line into storm line. You know,
no,
if all of them are going to treatment plants, it's understandable. Like this, what you have on the screen now, you can see it's not exactly what it is, but it's more close to what it is. That during dry weather flow, the foul sewer will just flow. Then when storm comes, storm will join, and then when they go to combined sewer overflow structure, the bottom outlets will go to treatment plants, while the clear water will go back to the open stream. But as I said, it's a rare combination because of the maintenance and those that will man it. And most time the machine is automated. Most times they are automated. Unlike here.
So there shouldn't be any reason for you at all to say you divert what do you call it? Foul sewer to
storm.
A storm sewer to a foul sewer. Maybe to some say you want to use it to aid flushing or flow.
No. Okay. The major reason is for the health of the water body. You know, we are in a country where we don't pay attention to those living downstream. We just care about ourselves. In some of these countries, one river flows to another river. So those countries that are on downstream, they'll keep, you know, the upstream countries on their toes. Or even in a place like Germany, for instance, you know, they practice a federal system. In fact, their system is so cascaded. Is so cascaded that local government reports to state reports to federal. So most times one river flows from one state to another one. So like the Bayelsa people now, I mean, people in River State or people in Edo State will pollute the water, and the Bayelsa man is using the water for drinking or for treatment. So you see that the Bayelsa man will be the one receiving the contaminated water. So where you have such cascade of structure, they pay more attention to the health of their water body. So that's why on no account was sewer.
But there's effluent standard now. Is the effluent standard not met?
But who monitors the standard? We're looking at our own scenario, sir. Okay, in those areas, effluent standard of, let's say, BOD of 18 milliliter per liter.
Yes.
In Nigeria, who maintains? I mean, Lagos is at downstream. A straight upstream might not meet that standard. and then the one downstream. I mean, what I'm saying in essence is that we don't have effective regulatory systems to monitor the effluent standards.
Well, Nezra and is a component you're supposed to be doing this.
Sir, I've been to Whooper treatment plant, and I can tell you this.
It's okay. It's okay, sir. It's okay.
I've been to treatment plant, and I hope nobody is from that here. But what they do is funny. When it's storm, they divert everything to the open stream, to the Abuja.
You're right. Even EPZ here where I am, even the EPZ here where I am, that's what they do. We quarrel and quarrel and quarrel.
And that's
there's no government regulation in that regard. There's no government regulation.
Yeah, exactly. Yeah, but we'll keep pushing to do the right thing and learning the right thing.
Yeah, you're right. It's okay.
Okay. So this I will telling you red eye angle, you know, the maximum bend tolerable. So all these ones, I think we'll read and understand them. All about hydraulics.
Yeah.
I'm looking out for those things that that might worth explaining. That's a Weisbach formula. Okay. Okay. I would like to give us 10 minutes break. Let's just have a small break. That's in between the class. When we come back, I think we'll move to the rational methods. And anywhere we stop, okay, we'll continue. Whatever that is here subsequently is something we can learn. We can learn anything here. This is a storm a overflow structure. You see, there's a level that this water will get to. It will overflow here, and this is like a separator. What you have on the screen. If it flows, it overflows. So these are just things that we'll read and understand. So I don't want to. Okay, this is the outlet structure. Okay, where the storm water enters the main body. Okay, this will tell us about pumps that you use in wastewater, just for you to understand. Rotary pumps. You know why these things are all included in this thing is that when you say you're water professionals, you are meant to be familiar with the terms and terminologies. So some of these things that are included here are just for us to get familiar with the terms and the terminology, so that when you speak, somebody will not have any doubt of your knowledge base. So we're going to take a 10 minutes break. So we're going to come back by 5:20. With the opportunity to change to 5. It's really heavily here, but I know that network will not be an issue. So I will see us in the next 10 minutes, and we'll start with rational method. Let me lay the foundation for what we're going to be doing tomorrow in the next 1 hour. I don't want it to be all theory. But the remaining thing, please, if you don't want to go for break, why not just scan through them? And so that when I come back, you ask me some questions based on what you've seen. So, gentlemen, I'll see us in the next 10 minutes, please.
Hello, sir.
Okay.
Yes.
Please, I sent a message saying I don't have those materials yet.
I will send it to you, sir, now, please.
Thank you very much.
I will send it. He's running here, so let me make sure we don't have a break in transmission. So, 10 minutes.
You can also, hello, sir.
Yes, sir.
Yes, you can also place your WhatsApp and call number. You know, it will.
So for the sewer design, your focus will be wastewater or the sewage, which is Q will be made up of the dry weather flow plus the infiltration flow. While the dry weather flow is the wastewater flow plus the inflow from other sources, unaccounted for. Then for the combined wastewater flow, it is now the dry weather flow plus the runoff. Then for the wastewater, there is denoted as W. It can come as liters per capita per day. This is just like wastewater demand per capita per day, which is about 100, between 100 and 150, before you apply your safety factor. But if you do it in terms of catchments, at catchment level, it becomes liters per capita per day. So here you're talking about what's the wastewater flow per hectare. Okay, Of course, we all know that 10,000 square meters equals to 1 hectare. It can also come in a factory, in a manufacturing sector. You talk about liters per production unit per day. So these are different parameters to come. Whereas the rain intensity is measured specifically in liters per hectare per second, because now you're talking about area measurements. So total discharge Q can come as meter per second, which is a list, meter cube per second, meter cube per hour, meter cube per day, which is a daily flow, meter cube per annum for annual flow. These are examples of wastewater production all over the country, all over the world. Okay, I think now it's revolving around 150, but you can see that some countries produce more wastewater. And trust me, US is taking the lead, because I know that US, they know how to waste water a lot. Farm, fishing, swimming pool, what have you, washing cars. While countries like Belgium, Germany, they are using very far less. So why do you need this? Because this is what you use to estimate your sewer flow. Then, the specific production of wastewater depends on the size of settlements, types of building, and the wealth of population. And it varies between 150 liters per capita per day to 250 liters per capita per day. So in other words, you are expected to generate between 100 and 250 liters of wastewater per day. So he said nowadays about 130 is the average. Then, and how do you calculate this? Population equivalent multiplied by the unit wastewater generation. So if I'm designing for 10,000 people, all I need to do now is to, like in a 3-bedroom flat, in a 3-bedroom now, is about, let's say 20 persons. So I multiply 20 by the wastewater production of 1 person. So, and so on and so forth. Then these are just caution that should be taken, what you should not do. For instance, things that should not be discharged into the waste system. I doubt if anybody in Nigeria complies with this. You should not put oil and fats. You should not put detergent and disinfectants. You should not put animal feces. You should not put vapor and gases. You should not put hardening substances. You should not put solid waste inside. So I think we will also understand them. Then these are the units wastewater production for hospitals, schools, and what have you. I want to take a look at the one for schools, which is very, very poor, very small. Why? Because in school, they don't produce a lot of wastewater. All they do is maybe they go to use the convenience, and they don't take their baths, they don't cook, they don't do a lot of things. But in the hospital, you can see that a lot of washings need to be done, a lot of sanitation need to be done, and so on and so forth. So all these things are, when you're doing your design, you go call up these charts, pick the appropriate value, and then you continue your design. Then for infiltration water, what is infiltration water? This infiltration water is like a safety factor. We expect that outside the wastewater we're generating from our homes, from our houses, there could be other wastewater that can come into our waste systems. So you have to factor them in. Okay. So that is that. And we have come to the end of the foundation for this course. So now we're going to go to our exercise for today, which is the rational method. I have less than 30 minutes. I'll just do the introduction, introduce the parameters, and then anywhere we stop, we'll continue from tomorrow. So this is the exercise we're going to be doing. the major exercise for this course. This is the catchment. This is the catchment you are given to solve, and we're going to apply the rational method. The rational method only has the limitation that once the area is more than 100 hectares, it becomes less accurate. So far, that is what's applicable. That's what most people use, and that is what I will introduce us to in this class. It has limitation. The limitation is that when the size of the catchment is getting bigger, it means that the time of concentration is getting less accurate. It means the time it will take the flow from the furthest point to the outflow will be greater than 15 minutes. And anyone that is more than 15 minutes is not contributing to runoff. I want you to just see that this way, that if water will flow overland for more than 15 minutes, half of it will infiltrate. As in, before it gets to drain, I don't mean on the inside, while it's inside the drain. I don't mean when it's inside the drain. Before it gets into the drain, for it to flow for long. Sorry?
Did you say 100 hectare?
Yeah, that's the limit for in using this method. It's not advisable for a land size that's more than 100 hectares, since 500, for you to use rational method. But what people do is that you build in some safety factor. Maybe if you get 1.2 as your drain size, you increase it to say 1.4 to take care of those errors. But that is the universal method that's being used so far. But that is the limitation. I'm just pointing out the limitation of it. 100 hectares, it becomes less accurate. Not that it's no more accurate, it's the accuracy goes down.
What if you discretize the
God bless
catchment?
you. Thank you, sir. But if you're discretizing, that means you're going to have many poor points, many outfalls.
Yeah.
I don't know if you understand.
Yes.
Any other question, please? Okay, now, this is a training. This is an online training. This sample I'm giving us now, it looks so simplified, but in real life, it might not look this way. It will look
I don't
complex.
take care of you.
It will look complex. It will look a bit more complex. But for the purpose of this training, we decided to choose something that is simplified. So these are different catchments. So what I want you to do is I want you to imagine these catchments as districts, different districts and sub-districts. The shape are uniform, but in real life, they will not be so uniform. But the concept, the principle, the methodology of solving them remains the same. So we're going to start with Siwa. We'll start with Siwa. So when we start this, when you are given this kind of work, the first thing you do is to call it out in a table in this form. Call it out in a table in this form. The conduit name, the start, the end, the length, the slope, and the area that that's bordering it, or that is serving, the area that is serving. For instance, look at this catchment A. This is catchment A, and we have one main sewer passing along it, across it. So that sewer, we call it sewer A. Why the catchment is catchment A? The end of the node is 2.3. The beginning of the node is 2.3. The end of the node is 2.2. So it's easy for me to know the slope, because slope is vertical over the horizontal. So if I know the length of this pipe, and I know the invert level here, and the invert level here, so I'll subtract the invert level here from the invert level here, divide by the length of the pipe, that'll give me the slope. Because for you to size this pipe, the slope has influence on it. I know that our major parameter we're looking for here will be the discharge, the Q. But when you go to your rational charts, when you go to any of the charts you're using, you have to provide 2 parameters, or even 3, but 1 is always fixed. The pipe material, the coefficient of runoff of the material is fixed. If you're using PVC pipe, 0.1. If you're using ductile iron, 0.4. If you're using concrete pipe, from 1 and 1.5. So those ones are fixed. So the other two parameters that are not fixed is the slope of that pipe and then the discharge. So with the slope and the discharge, you can size your pipe. So when your surveyor is working, your surveyor should take the coordinates, the spot heights, it depends on how what you guys agreed, 25 meters, 50 meters, 100 meters, whatever it is. We have to take it along the network, along the major networks. You have to take it. Now, when you bring into this paper, so this catchment A now, what's the size of this catchment A? Is about 15 hectares this way. That is total. B is this. Look at B, you see that B is smaller. Then C is as big as A, and E is as big as C. So that's what you have here. A, B, C. So all the catchment areas must be captured. Then their slopes and their everything. Then the next thing you do is you prepare a table like this. Hold on. Oh, sorry. You prepare a table like this, fractional method here. You might prefer to call it calculation sheets. But this table is very important. You cannot do storm or sewer design without this table. You must prepare a table like this in Excel. It's important that you prepare a table like this in Excel. Now, this is just for about 10 pipe networks, but in real life, you can have up to 1,000, and that will be quite massive. So this is what it looks like. Now, let me just show an example of the one I prepared in one of the work job I did for somebody. Let me just show the one I did in Excel. Are you asking question or you just muted yourself? Okay, so this is the chart of this is from this chart I'm showing you now that I produced mine. So this is the chart I was taught with. What kind of English is that? This is the chart I was using teaching me. So here the first thing is the pipe number, the start and the end manhole. Then the area is the next. The area is the next, the area of each catchment. Then the third column is you now multiply to get the wastewater flow. You multiply the dry water flow, multiply by the area, and that will give you the flow. So let me see whether Excel have opened. Not yet, so let me open it again. Still opening. Okay. It's going to open. Okay. So okay. This is example. Can you? I know you can see my screen, of course. Yeah. Okay. So this is a table I prepared for.
You didn't have this
sorry.
We don't have this material. Right?
No. This I didn't share it. This is a outside, but it is from this. It's from this. It's from this that I produce this. Now, what I want to tell us this, and as I will say it in this training, if you want to do any sewer or stormwater work, just go online or Google. Just put stormwater templates, you will see like 1 million of them. There are so many of them. Just try it tonight. Put or say rational method table or stormwater table or sewer table template. But if you want this, and maybe later I can send it. But I generate this one. I just did it on myself. But then take note of this. This one is for stormwater. Okay, this was stormwater now, for instance. Now, these are like how I did it. I'll show you. So what I did now for the stormwater is that I prepared this in Excel, and the first one was to say the contributing area, the nominal value, which is the coefficient of runoff. I use 0.8. I agree with the clients. That's what to be used. Then this is my rainfall intensity. Then this is my Q. When you multiply this by this and this, you get this. This becomes my Q. Then this becomes like a safety factor to upscale it. So the safety factor is about 1.2. You know, sometimes when you do design, you just apply some safety factor just to upscale it a little bit so that you just be, you know, you're playing safe. But that must be guided by code and standard. So this code and standard is what I used was what they call in a pipe network. You're supposed to give something like a freeboard. If you're using a pipe, if you're freeboard, yeah. If the height of flow is exactly 1 meter, you are advised to provide 1.2 so that they won't be overflowing. The drain will not overflow. So even if the depth of flow from your design is 2 meters, you can produce 2 point something just to give that freeboard. So that was what I did here. Then and so far and so forth and so on. So
how do you bring that in to a pipe system?
A pipe system is that there's a code in German system that says your pipe should flow between 70 and 90%. Your pipe should never flow.
Is it flowing partly full or?
Thank you. Partly full. It must be the capacity. I understand where you're going, sir. The capacity must not exceed 90%. Then to optimize it, to have an optimal system, it should fall between 70 and 90%. If you do a design and your system is flowing at 20%, you're a bad designer.
Yes, of course.
If you now do and it's flowing at 95%, you're a risky designer in quotes.
Yeah.
Okay. So it should be between anything between 70 and 90%.
90
is tolerable.
Yeah. Exactly.
Okay. So this is just my take home for today is that for us to master how we came about this chart. I'm tempted to go online and just go Excel templates for rational method. I'll see a lot of things. You see what people have done, whole of work. It always follows the same sequence. But the only difference in this one is that we combined the sewer and the stormwater. So everything from here to here is the sewer. Hold on, let me bring my spot something. So everything between here and here is what? Is for wastewater. Then from here to here is my stormwater. And then this one is the combined. So in your own work, if you're designing for sewer, you can bring out this as a separate Excel. Then from here, they remain the same. From here now, you join from here now. From here, you join it back to this place. Then if it's for stormwater, you start from you eliminate these three, join this one to this one. So if you watch here, you see pipe, start, end. The next thing is coefficient of runoff. The next thing is area of impervious. This is area imp. Then you sum the area up. Then you estimate the time of flow. If the time of flow is less than 10 minutes, you use the value for 10 minutes. If it's more than 10 minutes, you use the value. Then the duration of flow is this. The duration of rain, sorry, is this. Then this is the rain intensity. Then multiply rain intensity with the area of catchment, the impervious area, the reduced area. We call it the reduced area.
Excuse me, sir.
Yes.
The rain intensity, is it like, assuming we've done rainfall analysis, is it the EVIs we use, the extreme value intensities, or
Is the extreme values, the peak values?
is the extreme values? Okay.
The peak extreme, the same word.
Okay.
Peak values. Thank you. So now bringing it up to my design here now. Sorry. Drop it. Use it. Good. Bringing it up to my design here, you see, this one is for stormwater. You see that here, the first thing I did was to say contributing area. I want us to capture this because this thing is a work on its own. This thing is just the design itself. Before you now take this table, go to EPANE, swim, and then you model it and simulate it. So, but you must prepare something like this. So now, this is a contributing area. Is it 1 hectare? Is it 5 hectare? Then this is the coefficient of runoff. So in this our table, this is the coefficient of runoff. Look at it here. This is the coefficient of runoff. And I'll tell you how they call this. The coefficient of runoff is 0.37. The coefficient of runoff is 0.37. In this one, we use 0.8. Here we use 0.8. Okay.
Well, what if you have a heterogeneous catchment where you have to find a composite? Homogeneous.
If you have heterogeneous catchments, you use the mean weighted average.
Yes.
So that mean weighted average is somewhere.
No, it's okay. It's okay.
No, I have it. It's a good question. If you have a heterogeneous catchment, this is what you do, sir. You do
no problem.
You catchmentalize it. You list their irrespective
it's okay.
And use mean weighted average to get the average that you now use.
Okay.
So for any particular catchment, you use different coefficient.
Yeah.
For instance, in Abuja, Maitama might use 0.68, Use 0.75, but Lugbe 0.5. Then Kuje 0.4, Gwagwalada 0.3. Because Gwagwalada is a farm area, is a green area, is a farmland. Then Lugbe, Kuje is an upcoming area. So I can say 50-50, 50 built, 50 unbuilt. When you come to Maitama and Asokoro, then I will be going towards 1, meaning that every stormwater will go into the drain. That's just the layman's definition of that coefficient.
The place completely built up.
Now, let me even tell you something. This coefficient that I used here was at the instance of the client, the person, not the client. I mean the person that have the main job.
Okay.
He says 0.8 for him. He's looking at 50 years time. In 50 years time, let them build hell. The place will not be over. It will still fall in.
Okay.
Then, when we now say effective area, this effective area now is if you multiply the total area, multiply by the coefficient, it will give you the effective area. So, and that is what we did here exactly. Here, if you multiply this coefficient times this original area, 15.63, you'll be getting 5.8. You'll be getting column 8. Then in this place, in this Excel, I call it reduced area, effective area. But some people call it reduced area. In fact, I called it a reduced area ab initio. The person said no, change it to effective area. You can also call it the contributing area. It means that is or you can even call it the impervious area, knowing where that is the impervious area that contributes to runoff. So you can use any terms to call it. Then, this is my area, this is my intensity. Remember CIA. So I've already factored C inside this one. So CAI will give you Q. CAI will give you Q.
Please, I want to ask a question.
Yes, sir.
What was the basis of this intensity? You pick 140 millimeter per hour. So what's the basis?
The basis that this design was for Abuja. So we went to the highway design manual and we searched for Abuja. We didn't say Abuja. So I saw Bida. Is it Bida or Mina? Watch me now. So we used 10 years. 10 years return period. So when we want for 10 years now, 10 years in bidder. This is bidder, but not bidder we use. Bidder is about 5 years, sorry. 5 years return period is 150. Then we went to Lokoja. Let me look for Lokoja. This is Enugu. This is Ikeja. This is Ilorin. I think it should be in the second one. But that, okay, this is your Lagos. I don't know if you're coming from Lagos for C and A people. So for Lagos, for instance, now, 10 minutes for Lagos is 130 for 2 years, 160 for 5 years, 180 for 10 years, 210 for 25 years, 240 for 50 years, and 260 for 100 years.
Okay, thank you for that.
Is it clear now?
It's clear.
So
we normally use 150.
Who use 150?
150 for Lagos.
Okay, for how many? For what year? For what return period?
I think like 2 years.
Okay, let me check. Who gave you 150? Okay.
That's the normal. That's the information we got from
who gave you the information?
Well, we have that as a template. That 150 is.
Who produced the template? This one is the only one recognized by Korean.
So let's cross check it now.
Okay.
Lagos.
So for
hello, engineer.
Yes, sir.
Yeah. I think
it's about 130.
I'm with Chitu.
Okay.
So it's our organization process asset. So it's our properties.
Wonderful.
Over time.
You're in order, sir. You're in order. You say 150. This place they say 130. So if you ask me to choose between 150 and 130, me too, I'll choose 150.
So, but it's okay. There's another approach also. If we have,
but he said 2 years. I doubt that is 2 years. I think it should be 5 years, sir. And 5 years is about 160. Yeah, it's about 160.
Okay.
So what I'm trying to say, hello, sir.
Thank you for that.
To those who are in Lagos, hello. Those who are in Lagos, you can recollect that in July this year, maybe July 15 or 16, a Friday like that, that we have almost heavy downpour, and that's rain for very long hours. You understand? In Lagos and everywhere we're flooded. So, and I think that might be one of the peak period, which I think the return might be in Lagos. You can predict that the return can be in another 2 years. If you agree with me.
I agree with you, sir.
We do experience that once in a while. So.
Yes. I think Lagos people should be designing with 10 years, which is almost 180. If you ask me, only that it will be expensive, of course. So 150 is modest. 150 is okay. But even the higher, the better.
Okay, that's clear. Thank you.
All right. Now, back to where we are. So that is what I just want to explain. If the catchment is not homogeneous, you need to use the mean weighted average for you to generate your what do you call it? Your coefficient of runoff. So look at what I did here. Kaduna, it was 130 for 10 years. It was 130 for 25 years, 150. Lokoja, 140 for 10 years, 25 years, 160 for 25 years. Mina, 150 for 10 years. For 25 years, 170. So 10 years for Abuja cannot suddenly be 1,000. It has to be between 130 and 150. So we choose 140. Okay. Then for runoff determination, how did I come about 0.8? Well, let me tell you something I did. The client has already set 0.8, but we needed to justify it. So I did backward engineering. So for the green areas, we assume that the green areas will constitute 20% of the whole built area. When the place is finally built up, that there will be 20% green area. If you don't agree with me, please just say. Then we also assume that the roof area will constitute 50% of the built area. And the factor based on the table, I'll show you the table, is 0.95. The green area, the runoff coefficient of green area is 0.2. The runoff coefficient of roof area is 0.95. The runoff coefficient and the roads will constitute about 20%. And that will be another 0.595, sorry. Then others unaccounted for, maybe lawn, playground, whatever, will be 10%. And that will account for, and the equivalent of it is what? 0.6. If you take the mean weighted average, if you click here, you see the formula for mean weighted average. I don't know if you can see my address bar. There should be somewhere. I now took the mean weighted average to be present to become 0.8. So that's what it is. So that was why I was trying to tell us about how to get your mean weighted average by, okay, here. So here, let me just show you where we did it. Okay, look at it here. So you use summation of their individual peak runoff and area divided by the total area. You get your mean weighted average. Okay, let me remove this eraser. Okay, so I was still explaining the chart because that's where we stop for today. Tomorrow we'll enter the rational method proper. So what I will do is at the end of this class, I would like us to Google and come up with your own templates online. Like I will send you my own. Before I send you my own, I want you to generate something like this. Get something like this in Excel so that you get master that you are typing tomorrow, you're just keying in, because if you're looking at it like this, it's not too clear and it can be confusing. But let me explain to you. So here now, this is what we are designing. We're designing for this catchment. And the first thing I said is that you bring it into a table like this. And that's exactly what we did here. Let me even look for the one. Sorry. The areas. Yes, this is it. This is the catchment. Okay, no. Section analysis. Yeah, this is it. So look at it. You bring it into area. This is subcatchment. This is the area they are covering. This is the coefficient. Then the effective area. Then the duration. Okay, we use 15 minutes. Then the rainfall intensity. Then the discharge. Once you get to the discharge, you finish solving your problem is solved. So then, back to the rational table. So if you list the pipe, their start node, their end node, then the area of this one is 15.63. Now we're talking about C1 now. You multiply by the dry weather flow. How did you get this dry weather flow to multiply with this? This is how we got it. This is how we got it. This is for the storm. Then other parameters. Design storm here is 10 minutes. The population density is 100 capita per hectare. And that's for low density, of course. The water consumption is 130 liters per capita per day. The peak factor is 2. The parasite water is a standard, is 0.1 per liter, 0.1 liters per seconds per hectare. Then the pipe roughness is 1.5. That's for concrete pipes. That's for concrete pipes. So these are the parameters we need to do our design. Okay. Then when you finish those parameters and you get your Q, pipe sizing will now depend on the discharge, the slope, and the roughness. And the discharge will be the wet flow, the maximum dry weather flow, plus the storm water flow. That's for the combined anyway. How did we get the dry weather flow? The dry weather flow will now be the wet water, the wastewater flow multiplied by the population density, multiply by the factor of safety, then you include the infiltration constant, which is just a kind of a value to take care of unaccounted water. Because sewer lines, we often see that there are water that comes into the sewer lines that are not designed ab initio. So the code provides for you to bring in 0.1 for liters for every hectare as infiltration water. So to get the dry weather flow, you multiply the wastewater, the specific wastewater flow by the population density, convert it to seconds, multiply by a safety factor or peak factor, and then add infiltration flow. You will get the flow per hectare. So this is the flow per hectare. For the stormwater, yes?
Please, I want to ask, is there any guidance on the population density?
Yes, there's guidance. Number one, if it's a built-up area, you use empirical evidence. Say, how many people per household? Multiply by number of households. If you come to a street and there are 3-bedroom bungalows, like what we did in water design, if there are 3-bedroom bungalows, 100, if there's a mini estate, let's say, each household is about 10 persons. So 10 persons times 100 houses in the estates, that becomes 1,000. So your population density becomes 1,000 per capita.
Okay.
If it's a virgin land, then you ask yourself this question: what is the land use of that area? It's one important question that we don't ask in this part of the world. That is why sometimes you see that infrastructure will overgrow the development. But Lagos is a organized system. If it's Lagos, because if you come to an area, the government would have designated this place. It is also in Abuja anyway. Low density. Low density means not more than 200 people per hectare. Medium density could be not more than 500 people per hectare. High density could be not more than 1,000 people per hectare. So for you to meet some of these requirements, it means you need to go vertical. That's why some places in Abuja, you cannot build 2 floors or 1 floor. They must ask you to build 4 floors, 5 floors, because those places are designated as high density area. I remember when I did something for somebody in Kuje, he did a design for 2 families. They went and asked him to change it to 6 families. He didn't understand what they mean, but me, being an engineer, being a water person, I understood that that place was for medium density. It means more number of persons per unit hectare. So this is what I want us to understand now. This is how thank you, sir. This is how we generated our discharge per hectare for the sewer. So you can see that we make use of the wastewater from household, which we assumed to be 130 liters per capita per day. But for the stormwater, for the storm system, the first thing we did was to say, what are we designing for? Are we designing for storm, surcharge, or flooding? Is it a rural area? Is it a residential area? Because this is the formula we want to apply. We want to multiply the rain intensity by the area of impervious. If you break area of impervious into 2, it will give you the catchment area multiplied by the peak runoff or the runoff coefficient. Please, some terms can be used interchangeably. So is it the peak runoff, if I do the peak runoff multiply by the area of that catchment, it will give me what we call the area impervious. And that is column number 8. Remember, this is where we are for the storm. Column number 8. Number 7 is the peak runoff. So if you multiply the peak runoff times the AC, this is the AC, column number 4. Gentlemen, have we opened this chart? I think everyone should open this chart. We're closing this class in the next 6 minutes. Open this chart so that let me get you this, so that when you're downloading your own templates online, you will begin to select the one that fits into what we are doing today. So this is the area, the total catchment area. And now this is now the effective or the impervious. After multiplying the coefficient runoff, what is this coefficient of runoff? It simply says this is the ratio of the whole water that is falling on this catchment that will constitute runoff. It means it is not the area, all the water that fall in your compound that will flow into the drain outside, unless you built in the wrong place, because it is only the water from your rooftop. Other ones are meant to infiltrate. That is why many years ago in Abuja, when you bring a plan for approval, they will ask you that the footprint of your building must be less than 40%. What they are trying to do is that they are trying to make sure that the individual plot, the coefficient of individual plot, does not exceed the overall coefficient that was used in designing Abuja. They probably must have used 0.6 or 0.7, meaning that in your plot of land, your roof footprint must be less than 50%. The other area should be green, flowers, so that when this rain comes, majority of it, or 50% of it, is expected to infiltrate. Then only 50% will generate surface runoff. But if you are the type that will go and seal up everywhere, unless you do it illegally, but if you bring it to a approving authority, they are not meant to approve such. And that is also why, if you look into the city, both here in Lagos, you'll find out that they are meant to be green areas, some swells, infiltration basins. Some of these areas we see in town, they are green, plain food. We don't know what they will serve. They serve purpose of providing what they call infiltration basin for storm to infiltrate, so that the quantity of water that will run overland, run on the surface, will be greatly minimized. It will be reduced to a large extent, so that the drain that have already been designed will not be exceeded. So back to where we are. So if you multiply column 7 by column 4, you get column 8. Then column 8, you sum it up, you aggregate it. I will show you that tomorrow. It will now get you column 9, which is now the summation. And when we say this summation, what do we mean? Let me just explain to you now. Look at these catchments. If water is not flowing out of anywhere around this place, it means that catchment A will empty itself into catchment B. It means catchment B will empty itself into catchment D. It means that catchment D will empty itself into catchment F. So as it's going downstream, is increasing. The area will be increasing. And as the area is increasing, that is how your discharge is increasing. And that is why if you have been doing design, you find out that as you are getting towards the treatment plant, your pipe size is increasing. As you are getting towards the treatment plant, the reverse is the case in potable water. As you are leaving the tank, your pipe is decreasing. So that is what you see in column 9. So column 9 is now the summation.
Why is that case reverse in potable water?
Good. Now, why is the reverse? Is that in potable water, the tank is the source. So as water is going from the tank, going downstream, is branching off. So the mainstream, the primary line, the main line will be reducing in quantity, in number. It will be reducing because it is giving out tributaries. It's branching off. But in the case of sewer, as it's heading to the treatment plant, it's collecting inflow. It's getting inflow. So it will be increasing in size until it gets to the treatment plant. It becomes very big. Whereas for the potable water, is outflow, is flowing out, is distributing water to consumers. Is that okay?
I see. Thank you very much.
Okay. So our small job is for us to master this table, because this is the basics for rational method. So after you do, this one represent the time of flow. So you can see that this time of flow is about 250 seconds. So we use the value for 600. And that 600 means 10 minutes. So these three columns, column 10 and 11, are just the same. After that, you go to your IDF, your rain data, and call out the rain intensity, which is already in liters per seconds per hectare. You convert it. That millimeter per hour, you convert it. Depending on the unit you are working with. This is the value. So if you multiply the rain intensity with the summed impervious area, you will now get your Q. So we multiply this by this, you get your Q. So this is now the end of stormwater here. So all these other ones now, forget about this wastewater flow. This one is now for a combined system. So for combined system, you now add this Q for storm plus this Q for sewer. For now, please just ignore column 14. If you look at it, you find out that column 14 and column 13 are almost the same thing, because it's just that we are adding now the sewer as a safety factor, it's a safety measure anyway. After that, you just repeat the length, the slope, which you have already called out. Then you divide by 0.9 so that to meet up the 90% flow I talked about, to have a free board, 10% free board. Then you go to your charts and you read your charts, and we discover that the pipe size will be 800 millimeters. And so on and so forth. So that is, then here is velocity. So from the charts, you read out the velocity, yeah, you read out other parameters. But technically, our job stops at this diameter. All these other ones are for academics. It's for academic purpose, just to ensure we call check. Like here you can see there's two velocities. This is the velocity based on calculation, and this is the velocity based on charts. So, but as I said, once we get to diameter, you stop. And if you look at the table I showed you, once I got to the diameter, I stopped. So while you are seeing, look at it. When I got to diameter, I stopped. After the discharge diameter. So any question? Any question? Do we have any question? If there's no question,
hello.
Yes, I can hear you.
Hello. So
Yeah.
are we going to get the video of this training or presentation?
Let me just pause it now. Let me pause the video. You're gonna get the video at the end of the training.